Yes. Okay. Okay, so let us start with the exercise that we left in the last session. So have you thought about it?
There's a reduction from HP to EQ.
Yeah, that's fine. But what is the reduction?
Well, we construct sig given m hashtag x. Uh, okay, fine. You're using MNN here. Can we use different symbols because
Yeah, we have to use different symbols.
so
So the suggestion
yeah,
is HP. Okay, maybe I change this color. HP to equal. So from M hash X
to
to Turing machine. So let us call them N1 and N2.
yes N1 and N2, N1 and N2.
Or M1, whatever. So you have to specify the behavior of these two in terms of M, X, and their private inputs.
So we'll have another Turing machine that has N1 and N2 as inputs, right? That's the reduction.
Yes.
Yeah.
So
So
a description of N1 followed by a separator followed by a description or encoding of
N2.
yeah.
So for let the new machine be N and
No,
N
there
has
is no,
M
no, no,
hashtag
no,
X.
no, 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 no. Don't run this. Just prepare this and then you are done.
Oh, okay, fine. So yeah, so N1 and N2 accept sigma star if M accepts if M halts on X,
Yes.
and if M does not halt on X, then okay, fine. It doesn't work, does it?
Yeah, that's good. N1 will still be sigma star, but N2 will be something else.
Yes.
So that's nice idea. Okay. So if that is the I would say uh, design choice, M halts on X. In that case, language of N1 and language of N2 will be sigma star. They are equal. And if M does not halt on X, language of N1 will continue to be sigma star, whereas language of N2 will be
Fine.
something. Okay. So, irrespective of M's halting on X, N1 always accepts sigma star. So I can definitely design N1 like this on input V1, accept and halt. Okay, so this is the behavior of N1. It does not depend on the halting or not of M on X. What about N2?
And N2 will simulate M on X.
Simulate M on X.
If it accepts, then accept whatever in except V2. And if it does not halt, then N2 will also not halt, and so L of N2 becomes 5.
The simulation halts, accept and halt. So what will be this in this case?
5.
5. Okay. So just think, what is the input, what is the output? Okay. And also the fact that a total Turing machine given this can generate this and halt after a finite amount of time. Irrespective of whatever M and X is, it will generate this N1 and N2, description of N1 and N2, and halt. So that's about reduction, right? And you convince yourself that this machine and this machine, given a description of M and X, can easily be generated. Okay, so this is clear, right? This machine is very clear. For example, you may take the accept state as the same as the start state. Okay, so in which case, immediately after the machine starts its operation, it essentially goes to the accept configuration. Okay, and this one, so keep all the transitions of M on X, add some few extra states, like for copying copying X to some tape. Okay, so N2 will start at some new start state S prime. It will copy this X to some tape, and then it will switch to the old start state of M. Then that will be just a simulation of M on X. Whenever this reaches R or T or R, then this comes to something like a new accept state. Let's say T prime. Okay, so this is the only conversion that the reduction machine will have to do. Okay, so we'll usually not specify how this is done. This is obvious. Only you have to say what is the behavior of the output machine on its private input. Okay. Okay. So if there are no questions, so we will move to the next part. This is fine, right?
Yes, sir.
Okay. So today I hope to cover another way of arriving at this, but in a much simpler way, using what is called the Rice's theorem for a pair of Ari languages. But anyway, let's see. It is not recursive. That is fine. But is it recursively enumerable? What does your intuition say? This is the first thing. So this is the language. They have exactly the same.
Not RE.
Intuitively, it says that in order to decide this equality, I have to simulate M and N on all possible inputs. Right. That can be done on a time sharing basis. Right? That's not a difficult issue. But you have to check all possible strings and the fact that M and N agree on all possible input strings. And these machines M and N are allowed not to halt. They may loop. Therefore, in any finite amount of time, you cannot simply decide whether these machines are looping or something like that. Moreover, there is an infinite number of strings on which you have to decide.
Sir,
that this is accepting the, yes.
sir, suppose I know a language is not recursive and I know it's co-RE. So that does not immediately imply that it is also not RE.
This reduction proves that this is not recursive.
And I also prove that it is co-RE separately by providing the TM.
You may, if that is the case, if this is, yeah, no,
It is
first of all,
co-RE.
it is co-RE. Is it co-RE?
If LM is not equal to LN, then like the first time a string belongs to M and not to N.
Yeah, then you can find out
Immediately we
eventually.
accept that.
Yes.
And since you're doing on time sharing, this will come up sooner or later.
Yeah, so what you have currently, this is not recursive, therefore its complement will be,
It is not recursive, but its complement is recursively enumerable. So EQ must itself be not recursively enumerable. Otherwise, the not recursive condition
yeah.
is
Yeah,
invalid.
that way also you can do. That way also you can do. Yeah,
And
that's
in
also,
this problem, it's silly, but sometimes it is not so silly.
yeah. Yeah, so that's okay. That's also fine. But what I would like to say, let us do an explicit reduction to show that this is not recursively enumerable. Yeah, that argument will also hold. The intuition is that you cannot decide this by simply simulating things. Okay. And apparently there is no better way of checking this other than simulating. Okay. So if you have to prove that this is not recursively enumerable by reduction, what should be our natural choice? SP complement, right? So it will be something like this. M hash X will be converted to encodings of two machines. Once again, let us use the same language, same notations, N1 and N2, such that if M does not halt on X, then language of N1 implies language of N2 will be equal. And once again, you may take this as sigma star. And if M does halt on X, let us again take ln language of N1 equal to sigma star, whereas language of N2 is anything other than sigma star, maybe empty. Okay. This is fine, right? So N1 will be exactly as before. Accepts and halts. What will N2 do? I in particular take this example because this is once again a very, I would say, very prototypical reduction example. You have already seen, provided you have gone through the lectures. So this is a very, I would say, usual way of reducing from the complement of HP.
So can we flip things around?
It
As
means
means say m does not halt on x, then L of n1 equal to L of n2 is equal to 5. If m halts on x, then they are different, and then they are differing but not equal to 5. So I mean, if m does not halt on x, then it's easy to generate the language 5.
okay, so then this will just reject and halt.
Yes.
And the other thing that way also you can do. Yes, many possibilities are there. Okay, so that's also a valid reduction. And if halts on X, then maybe you can
then we
accept.
can just have a fixed set of
Or
strings
accept
and
and halt.
generate that.
Will be empty, empty, empty.
Oh, that is empty fold.
This will be sigma star. Yeah.
Yes.
That also you can do. Okay, that also you can do. Yeah, I hope you. This is a valid reduction. But if I want this, because I am just trying to give you an example of a very typical type of reduction. The idea is that if m does not halt on x, it does not halt in any finite number of steps.
No. Yeah.
Okay. So what finite number of steps will you take?
Number of states.
Not number of states. Maybe this will be
Length of input.
Length of the input. Yeah, of course, your reduction is perfectly okay, but I can also do this. Simulate m on x. This is not an infinite simulation. This is going to terminate. But these many steps. If the simulation does not halt, or if it is halts by this time, maybe you just reject and halt. Else, just accept and halt. Okay. So if this is always sigma star, if it does not halt on x, then it will not halt in any finite number of steps, in particular this. So it will accept and halt. The language will be sigma star. Okay. If not, if the simulation halts, so if m halts on x, let's say in s steps, so this s has nothing to do with the start state. I'm just using this s. Then this halting behavior is not noticed if V2 is not too large. Right? If you simulate for less than s steps, then you do not notice that this is going to halt. So in this case, this will be nothing but set of all V2 such that length of V2 is less than s. Happy or not? Yeah, of course, the other reduction idea is perfectly okay. But this is a very typical type of reduction. when you do it from the complement of HP. Is this fine?
Yes, sir.
Okay, so fine. So I suggest that we go to some new things. So this is based upon a personal communication from Deep. So this is a nice example. So I would like to cover this, spend some time on this. So let's see that L be a recursively enumerable language, which is not recursive. Okay. Now I will ask questions about some languages that I will generate from this L. Okay. So L is RE but not recursive. This implies the complement of L is not RE. Because if L is RE and its complement is also RE, then you have seen that it is recursive. Right? But we started with a language which is not recursive. So its complement cannot be recursively enumerable. Okay. So I will start with this. So this is a language. It may be, for example, the halting problem, HP. It may be MP or any other thing that we have already come across. Okay. So as an example, L could be HP, MP, some other things that you already know to be in this class. So what I do, I take all these strings in L and prepend a 0 to it. So what kind of language is A? Is it recursive, not recursive but RE, or not even RE? Okay, of course, you may ask the question, what is the input alphabet for this L? It may be anything. It may be 0, 1, it may be A, B, C. Anyway, it doesn't matter actually. What do you think?
A is RE.
A is RE, but is it recursive?
No.
No. So how do you prove it?
RE, we can just make a Turing machine for it, not recursive deduction from HP.
A. Oh. So of course, A is RE, but not recursive. Answer is correct. So I have to prove this. A is RE and A is not recursive. Okay. So if something is RE, then I have to show it is the language of a Turing machine. Okay. So I have to use, let me use the Turing machine for this L. This is given to be RE. So T is not a decider, but it doesn't matter. So I will generate a machine on input X. First check whether the first symbol of X is 0. That is an easy check, right? If not, for example, if X is empty or X starts with something else, some other symbol, 1 or hash or A, B, C, whatever, then this is not definitely in this language. Because every string in this language must start with 0. If not, what should I do? Suggest something. If not,
Checked immediately.
if not, somebody tried to say something.
Reject immediately.
Reject immediately. There is another option. What is that option?
Reject by looping.
Yeah. So here you can either reject explicitly or go to an infinite loop. Let us do the decent thing. Reject and halt. Otherwise, if it starts with 0, X is of the form 0 W, you simply simulate this machine T on W, and whatever the simulation result is, you just follow. accept if T accepts, or reject if T rejects. And one thing is obvious, if T loops, the simulation will also loop. So you don't have to write anything. So you can design a Turing machine. Of course, this cannot be total. To recognize this language A. And for the second part, the suggestion is that I should make a reduction from the halting problem. I don't know how easy that will be, because nothing is told about the exact nature of L. It's not an explicit language like this, right? Where you know what to prepare. So it's specified relative to some language L.
Can I do a reduction from L?
Yes, please, louder, little louder, yeah?
Can I do a reduction from L?
You can make a reduction from L, because L is already known to be not recursive. Okay, so you can take L. What is the reduction? This is a nice idea, because we have L at our disposal. So I can use L. So W will map to just look at this. W will map to my God. So why are you so afraid? This will not bite. Just tell something.
So 0W.
Yeah, as simple as this. W is simply mapped to 0W. So if it is in L, if W is in L, 0W is in A. By construction, if W is not in L, then 0W is not in A. Okay, so that's how reduction goes. Right. Okay. So that's it. As simple as this. There is nothing more, nothing deeper than this. Okay. Now if I do this, instead of considering strings in L, I am considering strings not in L. So I also can write it this way. 0W such that W is in the complement of L. Now, what kind of language should be B? Yeah, of course, this complement is with respect to the sigma star, where sigma is the alphabet for L. So, what do you think it will be? Tail or write something?
Sir, it will be not RE.
It will be not RE, as simple as this. So this is not RE. And you prove exactly the same way, because not L complement is not RE. I will reduce to B. So W will simply go to 0, 0W, right? So if W does not belong to L, then it will be in B. If W belongs to L, then 0W will not be in B. Okay, so that's a correct reduction. Okay, so this is not RE. Essentially, you just add some 0 or 1, some constant thing before a language, every string in a language. It is not supposed to change the complexity of the language, right? Okay, so now if I take the union of A in part A and B in part B, and if I call this language C, what kind of language is C? It's the union of a recursive, not non-recursive RE language and a non-RE language, but built in a very specific fashion. What is C? Okay, so let me write down clearly. So it is 0W such that W is in L or W is not in L. This is coming from the definition of A. This is coming from the definition of B. So what is this?
Sir, this will be recursive.
Yeah, that is true. But what is this? This is equal to
0W such that W belongs to sigma star.
yeah, anything. Okay, so this is nothing but 0 sigma star. And this is regular. And of course, by the hierarchy, this is context free, this is context sensitive, this is recursive. Okay, this is even regular. Okay. So, yeah. Now, this is the original question that was asked by Deep. So, instead of taking the union of A and B that way, I will add 0 to all strings in L, but add 1 to all strings in L, 1 to all strings not in L. And then I take the union. Okay. So 0, this is recursive, RE but not recursive, and this is not even RE. Because I have just used 1 instead of 0. Now what kind of language is this? So if I make this reduction, I am reducing from L, W will go to 0W. What does this prove? First of all, is it a valid reduction?
It's a valid reduction, but it doesn't prove anything.
It doesn't prove anything.
No, because if L, since we know that L is RE,
Yeah.
so if
What not
it's not
recursive?
recursive. It's not
Okay.
recursive, huh? It's not recursive to
This
begin
will
with.
prove. This is a valid reduction and will prove he is not recursive. Okay. On the other hand, if I make this reduction 1W, what does it prove? What will it prove?
It's not RE.
Okay. Okay. Okay, so I have taken this example in order to clarify certain things. It's not necessarily that you always have to do some reduction from HP or things like that. And yeah, so this is a nice example. So now let us play a little bit more on similar kind of stuff. So let L be a language over sigma. I am not currently mentioning anything, whether it's RE or not. I'm taking R as a recursive language. R stands for recursive. And I'm just considering L prime equal to L minus R. So this is the set minus. Okay. all the things that are common to L and R will be taken out from L, and whatever remains will be called L prime. And R is a recursive language. Now you will see some 4 statements. If L is RE, then L prime is RE. Is it true or false? Okay, so of course you can assume
True.
that. You can always assume that, because L is, in this case, L is RE. So R is a recursive language, so it's a language of T for a total Turing machine T. Okay, now if L is given to be RE, L is the language of M for some Turing machine M, not necessarily total. Okay, then you say this is true. Why? I have to build a Turing machine for L prime. Yeah, this is true. Why?
Because you can check, since L is RE, you can check if a string belongs to L, and since R is recursive, you can check if a string does not belong to R. If these 2 conditions are satisfied, then we are done.
Okay. So a Turing machine, a recognizer, not a decider perhaps, for L prime is this. Okay, so on input X or W, whatever you say, run. Of course, you can do the 2 runs in parallel, but you may first run T on X. If T accepts, reject and dot. Okay, because any string which is accepted by T must not be in L prime. You have taken out all those strings. Okay. Otherwise, T rejects, because it's a total Turing machine. It can never loop. Looping behavior is not present in T. Okay. So, accept or reject decision will come after a finite amount of time. Okay. Then you run, or here run of course means simulate. What did I use? M. And do whatever M does. If it accepts, accept. If it rejects, reject. If it loops, loop. Okay. So this is true. Okay, the second question is just the reverse question. If L prime is RE, then L is RE. Okay, so once again, let me write down. L prime is nothing but L minus R. R is a recursive language.
If string belongs to L prime, then it necessarily belongs to L.
Yes.
But so that way it is okay. but then that doesn't cover all these strings.
Yes. So what do you think? What does your intuition say?
It's not true, but counter example, yeah, that's the tough part.
Not true. Good. Yeah. How many? 22 people are there. Please say. Yeah, till we have to proceed. Okay, anyway, let me give you this. If R equal to sigma star, it's a recursive language, right? It is even regular. Then it says that irrespective of what L you started with, L prime will be empty because you have taken out everything. So empty set is definitely RE. But this says nothing about L, right? So I can, for example, start with L equal to not HP. So this is false. Agree or not?
Yes, sir.
Okay, so what about C? Of course, in part A, we have seen that if L is RE, then L prime is RE. But if I additionally impose the condition that L is not recursive, then L prime is also not recursive.
We use the previous example only. L is what? HP, R is sigma star. We are done.
So this is also false. R equal to sigma star. L is HP. So L prime is empty, which is definitely recursively enumerable, but it's also recursive. Okay, so this is also false. So that leaves us with the final question. If L prime is RE but not recursive, then what about L? This is RE but not recursive. So once again, let me write L prime is L minus R. Okay, so you think I will take a break for a couple of minutes. Okay, so what do you think? What does your intuition say? Yeah, tell something. What does your intuition say? Yes or no? Yeah, say something. We have to do some more exercises.
Sir, maybe it is true.
Maybe it is true. Okay, at least I can hear something from you. Good. Maybe it is true. How will you prove it?
Sir, can I do a reduction from L prime to L?
You will make a reduction from L prime to L. So that will prove. Okay, let's see. Suggested reduction. L prime to L. So W will map to
W.
W itself. That will not do because you have taken out something. So anything in L prime should map to. Oh, sorry. W to W. Okay. So then you have taken out certain things, right? So those things will also map to. So those things will not belong to L prime, right?
Yes. Yes.
But they will belong to L. So that's not a valid reduction, right? Okay, so you can have W in R, in which case W in R, W in L, then this is not in L prime, but W is in L. So this is not a valid reduction. Okay, at least I have seen some effort. Good.
Sir, then can I make a reduction from HP to L?
HP to L. How? L is quite a generic looking language. Is that reduction going to be so easy? I don't know. Because the output is a language, not a machine or something like that. So that way it's not exactly obvious how you can do it. Oops, 1221. I think I'm just in the third one. Let me tell you the answer. This is false. So you cannot prove it by reduction. So you tell me if this is false, what kind of counterexample can I produce?
So you need to choose L to be either not RE or total. I mean, recursive.
Okay. So there are two possibilities. AL has to be either non-RE or recursive. But you know, recursive languages are closed under almost everything. Okay, good. So if L is recursive,
So not RE.
yeah, L is recursive means R is recursive. So R complement is recursive because recursive languages are closed under complementation. Recursive languages are also closed under intersection. So this is nothing but L prime. This is also recursive. Okay, that violates this. So the only kind of example that you can produce is L prime is non-RE, sorry. L is non-RE, whereas L prime is RE, but not recursive. Is it possible? I said it's possible, so how? Hint. This one.
There you go. First part is
First part is RE but not recursive.
second part is not RE.
This is not RE. What should I subtract? This had theoretic sense.
Nothing phi.
No. I will keep it as that. Keep it as it
Oh,
is.
sorry.
Somehow I have to get rid of this part, right?
All strings that start with 1.
Okay. So maybe because I have used L here, so let me use something else. A, RE but not recursive. Consider this L to be 0W, W in A, union 1W, W not in A, R1 sigma star, the L prime is right. Convinced? Oh, sorry, I should have written it somewhere else. Okay, I will do it. Move it there. How select rectangle? Let's see. Okay. Happy?
Yes, sir.
Good. So this example was quite nice. Okay, so now let us look at something more on conventional applications of theory. So let CFL be the set of all Turing machines whose languages are context-free. First of all, use Rice's theorem to prove that neither this language nor its complement is recursively enumerable. So which part of Rice's theorem will you use? Part 1 or part
Non-monotone parts.
non-monotone part? So you have to use Rice's theorem part 2 because you are proving not RE.
It's definitely non-monotone if you shrink the language. But if you increase the language, it doesn't necessarily remain context-free.
Yeah, so going to a superset does not necessarily leave a language to be context-free and conversely. Okay.
Either way.
So for example, I can have a power n, b power n, c power n greater than equal to 0. This is contained in this. This is contained in ABC star. Right? This is context-free. This is context-free. This is not context-free. So this says that being a context-free language is not a monotone property, because you go to a superset, this property is no longer satisfied. And this says that being not context-free is also not a monotone property, because you start from not context-free language this, go to a superset, it becomes context-free. Agree? So this says
Yes, sir.
being context-free is not monotone. Whereas this says being non-context-free is not monotone. Okay, so monotone property is one which, if satisfied by some set A, should also be satisfied by any superset of A. Okay. Now these are the properties: being context-free or not being context-free. Okay. So neither is monotone, and therefore something like this. Okay. So Rice's theorem makes this proof absolutely trivial, but if you do not want to use Rice's theorem, then you have to do some kind of reduction. Okay. So I will just give you a brief hint. This is one that will prove CFL is not context-free, and this is one that will prove the complement of CFL is not context-free. And you use similar techniques, okay, as we have done in our EQ example. Okay, so I hope you can work it out. So for example, if I use this, I have to convert m hash x to n. M, this is complement, so does not halt on x. Implies this is context-free, whereas in halts on x implies this is not context-free. So what can be a possibility? So if M does not halt, you keep on simulating, accept nothing. Okay, so this can be empty. And if it halts, so what is your favorite non-context free language? Give an example.
So WW.
WW, good.
A and B and C and
And yes, anything you take,
probably.
anything. Okay. So you just first simulate M on X. If it never halts, then you never go outside that step. Okay, never go beyond that step. You are not going to accept anything which is accepting the empty set. Empty set is definitely context free. It is everything starting from finite. And if it halts, then you check whether the input is of the form WW or A power n, B power n, C power n, or whatever, which is known to be not context free. Okay, and then based upon that, you take a decision, accept or reject. So if it halts, then it is this non-context free language. If it does not halt, it is empty. Okay, and here I have to do just the opposite. This one. M does not halt. Ln is not context free, whereas M halts implies this is context free. Okay, so once again, the technique is very similar. Make a limited time simulation of M on X. Here I have made a complete simulation of M on X. Make a limited time. For example, if the input for n is y, so limited time means this steps. Okay. If the simulation halts by that time, Okay. So there are two things. It does not halt, it halts. If it does not halt, it should be something like this, not context free. Now you look at your input Y and find out whether it's WW. Yes or no? So if M does not halt on Y, it does not halt in any finite number of steps, however large this is, right? If so, you are just going to take a decision whether the input is of the form WW. Okay. On the other hand, if it halts, you simply reject, right? Okay. So it does not halt. And then based upon that, you accept or reject. And it halts, simply reject. Are you with me? So if M does not halt, it does not halt in any finite number of steps. Therefore, the language accepted is this WW language. On the other hand, if the machine halts, M halts on X, and what is the language? Okay, so halts, let's say in S steps. Only when you do not run the simulation for a fairly long time, you are going to accept. Right. What will be the language in this case? Sorry, 2S. S by 2 actually. Yeah, S by 2. Yes or no? Okay, so the limited time simulation may make an error in the judgment. So if you run the simulation sufficiently longer, then definitely you detected the halting pattern. Otherwise, you are, for some small inputs you are making, you are accepting or rejecting this. So is this clear? Now, is this language context free?
Yes, sir.
Why?
I think this has been done in class, if I'm not mistaken. No,
Very
this has not been done.
No, I do not think this is done, but it's very simple. Why is this context free? It should be like this. It should be context free. Why is it context free?
Finite language. Is it?
Yeah.
Yeah, since S is fixed, it's a finite language.
It is a finite language. Yes. This is
So
finite.
it's context free as well. It's regular as well.
Okay. So that's the idea. Okay, good. I think I leave this to you. Use some kind of once again use Rice's theorem. So use Rice's theorem. So I leave this to you. R means the reverse. Whether the language generated by M is the reverse of itself. Okay, so you do it. Yeah, this may be a good example. I should quickly say what I essentially mean. So I define RE square to be the pair of RE languages. Okay. So we can do a similar thing for part 2 also, but part 1 let us do. And a property of a pair of RE languages, okay, is a function P from this to true or false. Okay. And how do I specify a property? First of all, how do I specify a pair of RE languages? This is by specifying a couple of Turing machines. Okay, so L1, L2 is specified by the encoding of two Turing machines, M1 and M2, such that the language of M1 is L1 and the language of M2 is L2. Right. Or you can take unrestricted grammars, type 0 grammars to specify RE languages, but we will do in the machine way. Okay. So property is also specified by a pair of Turing machines such that their languages, when I apply this map P to their languages, I get T. Right. So properties are also specified by pair of Turing machines whose languages satisfy the property. Okay. So then, what is a trivial property? What is a trivial property? No, I think you are not looking at the lectures. But yeah, tell something. What is a trivial?
See, always true and all false cases.
Yeah. So trivial is T for all L1, L2. This is one trivial property. And is equal to false for all n1, n2. So the generalization of Rice's theorem for a pair of RE languages should be any non-trivial property of pairs of RE languages, or I may write it this way, RE square is undecidable. Right. So we have already seen any non-trivial property of RE languages is undecidable. Now I am saying any non-trivial property of pairs of RE languages is undecidable. Okay. So this is Rice's theorem for pairs. So how do you prove? Okay, so in other words, if P is a non-trivial property, let us consider this language. So to prove that this is not recursive. Okay, because you specify property by Turing machines. So I'm given you two Turing machines M1 and M2. I want to find out whether their languages satisfy the property or not. So this is the relevant language. Okay. So I have to prove that this is not recursive. So how do I proceed? I think this is, yeah, insert page. So I will propose a reduction from HP to this set pi. Okay. So I will map M hash X to M1 hash M2 as that if M halts on X, then the language of, sorry, okay. This will be true. And if M does not halt on X, then the property is not satisfied by their languages. Okay. Once again, as in the original theorem, we assume that this is false. If this is true, then you make a reduction from the complement of HP. And since this is a non-trivial property, it cannot be universally false or universally true. So I must have some RE languages for which this is true. Okay. So these are RE languages. So this is the language of some Turing machine M1. This is the language of some Turing machine M2. So I have to build two Turing machines M1. Okay, not a good idea. I use some different symbol. Maybe N1, N2. Okay. So I have to build two Turing machines M1 and M2. That is my job. Such that, okay. So N1 and N2 are fixed machines. They can reside in the head of the M1. So if M halts on X, in this case, language of M1 will be language of N1, and language of M2 will be the language of N2, and in this case language of M1 will be 5, this one, language of M2 will be 5. Agree or not?
Yes, sir.
Okay. And then this is a typical reduction, just simulate M on X. Okay. If the simulation never halts, this is empty. Okay, so that's what it should be. If it halts, you simulate this machine. M1 will simulate N1 on its input. M2 will simulate N2 on its input. And whatever that simulation says, accept, accept, reject, reject, loop, loop. Okay. Straightforward. Okay, so now using this, so we again look at this EQ language. So is it a trivial property or non-trivial property? So this is nothing but the language EQ of
Non-trivial because, well, not every pair of languages are same.
Yeah, some may be same, some may be different. Okay, this is a non-trivial property. In fact, if you slightly modify the notion of monotonicity for pairs, you see that this is also a non-monotone property. So this is not only not recursive, it is also not recursively enumerable. Okay, so how much time I do have? Just a little bit. Oops. This is also an interesting exercise. Let M be a Turing machine, prove that it is decidable whether M on a given input W moves left at least 2021 times. So I just give you a hint. Run M for how many iterations, for how many steps, not iterations. As there are a number of states plus W plus 2021. So you claim, I claim that running or simulating M on W for these many steps will let me decide with certainty whether M is going to move left at least this many times or not. Okay, if it does so, I am done. I will say accept. So simulate M on W for these many steps. Okay, if 2021 left movements found, accept, otherwise stop the simulation and simply reject. Okay, so once again you use some kind of pigeonhole principle and prove that if it has not moved 2021 times towards left, it will never do so. Some configuration, something is repeated. Okay. The idea is that after, if you do not make too many left movements, after these many steps, you essentially go to the blank portion of the tape. Okay. So you will keep on seeing blank, 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 blank. Therefore, if you run it for these many more steps, so some state will be repeated. And then that state seeing blank. Since that is repeated, there is no question of coming back. Right or no? Okay, is the idea clear? So I am just running short of time, so
Yes, sir.
okay, leave it to you. This is an interesting question. Once again, it's a little bit general, but A be a language, B be a language over another input alphabet. This is over sigma, this is over lambda, delta, whatever. And suppose that A reduces to B under a reduction map from sigma star to lambda star, which is onto surjective. When you prove that, I can propose a reduction from B to A also. Okay, so let us give a name.
So basically, it becomes a bijection.
No, not necessarily bijection. If I call this F, so it's surjective. So what does it say? Okay, it need not be
Okay, yeah,
bijection.
since every case is covered on lambda star side, we can just reverse the direction of the arrows.
Okay, so it's something like this. Yes, you are correct. So this thing maps to this. This thing maps to this. This thing maps to this, and similar thing. Okay, but everything has a pre-image, at least one. Okay, so I can propose a map from this to this. So if I take W, this will map to some pre-image. It's not very important. So does this make this reduction complete? That is why I have left this as your last exercise. Is it a complete specification of a reduction? Of course, I can see such a map G exists. Because it is surjective, everything has a pre-image. I can choose any pre-image and define the map G. So why is it that it is still not a reduction map? Okay, quickly tell. What else do I have to do in order to make it a reduction map? We are already past 1 o'clock. So what is missing?
If and only if case, like
No, if
you're
and only
pointing it on.
right? If and only if is not exactly a it is not a problem, right? Because this is a reduction map. So if this is in L, okay, if this is in, I would say B, then the entire thing must be in this entire pre-image. This must be in A. Otherwise, this is not a reduction map at all. Okay. Likewise,
The computability, like, is the map.
Exactly. So never forget this thing, that given W, a total Turing machine can compute GW and halt. Never forget it. The reduction cannot run forever. Okay. So now the question boils down to this: can a total Turing machine generate a pre-image of W under F? F is definitely something that a total Turing machine can do, because it's already given as a reduction, right? You just tell, and then let us stop.
It's a total Turing machine, so like either way we can reverse it.
Yeah, why? How?
Switch accept and reject states.
No. When we're talking about reductions, there is no question of acceptance or rejection.
Okay, they always halt.
It will always
It's only
halt computing this. Okay. So given any arbitrary string W in the lambda star, can you compute a pre-image after a finite amount of time?
Yeah, we like sort of check every string and then run the
Okay. So simulate W on every possible member of this. And this forward direction you can compute in finite amount of time. So check whether F of every string is equal to W. Whenever you find one, you are done. And you have to do it on a time sharing basis. And since this is surjective, one W must always be found. Right? Okay. So that's the idea. So this is an important thing. This has to be doable in a finite amount of time, maybe very large, but it's okay. Okay, so I think we stop here. I have only one small announcement. Next Friday is a holiday. So I would prefer to not disturb you on a holiday. So let us have a small tutorial session on Thursday. Let us shift the tutorial session to Thursday. That's all. And today I will post the last 2 hours of lectures. And that's all. We are done. Please look at these lecture videos, at least the slides. Otherwise, even conducting tutorial sessions is difficult. Okay, fine. So see you next week. Bye.
Thank you, sir.
Thank you for coming. And okay, so see you on Thursday. This will be a tutorial session.